let's try to relate between s, the linear distance, and theta, the angular displacement. So this discussion here is similar to what we learned in uniform circular motion, but there's a bit of twist to it. Okay, so again, I still have my same rigid body over here, which is in gray, and I place a black sticker to represent 1 point on the rigid body. Okay, I've already set my axis of rotation to be the center of the rigid body. So later, this rigid body here will be rotating with respect to this axis of rotation, or this pivot over here. So let's observe this rigid body here rotates for a certain angle. Okay, so my rigid body has already been rotated by about 45 degrees, and you can see that my black sticker over here, or this 1 point on the rigid body, has moved from some point which is on the x-axis. I've already moved into the first quadrant right now. Okay, as you can see here, my black sticker, as we mentioned in the previous video, is moving in a circular path. And because it is a circular path, you see that the radius or the distance of this point from the center of the circular path is constant. This radius here will be constant, and this point over here is actually the distance of this point from the axis of rotation of the rigid body. Okay, so let's clear out everything here. Let's define all the quantities clearly. R here, we have R. We also have S. From previous chapter, we also have S also. So S here is the linear distance, and you have theta over here, which was the angular displacement. Okay, so let's define everything in words. S here is a linear distance traveled by a point on the body undergoing circular motion. Any point on the body are all undergoing circular motion. Okay, no matter it's the point far away or a point near the axis of rotation, all points on the rigid body are undergoing circular motion. And S here is specifying for this particular point on the body, this is the linear distance that is traveled by this point of the body. It's not by this point, by that point, by that point. By this particular point, how much distance has been traveled by this particular point when it's undergoing circular motion. That is S. Okay, it's referring to a specific point on the body. Okay, R here, previously it was radius. It is still radius of the circular motion of this point, but to be more specific, because now we are talking about a rigid body, it's actually the distance of the point on the body. This point that we're interested in is the distance of this particular point from the axis of rotation or the pivot. Okay, R here now represent a distance. Distance of where? That point that we're interested in from the axis of rotation. Okay, next, theta over here will be the angular displacement undergone by the body from its initial orientation. Initially, you can see the rigid body is horizontal, but now it has been rotated by, let's say, 45 degrees. So this 45 degrees here is the angular displacement. So for angular displacement, I'm not specifying on any point of the body. I'm not specifying on any point of the body. I'm talking about the whole body itself. The whole body here, how much angle has been covered by this body when it is changing its orientation. Okay, so you can see that in red, linear distance refer to a specific point. This R here is referring to this specific point, but the angular displacement is for the it's general. It's for the whole body that is undergoing rotation. How much angle has it been rotated? Okay, so linear distance here, let's say it's pi. I'm just putting in some values into it. The distance from the axis of rotation, let's say it's 4 meters. Then the displacement and the angular displacement here, let's give it some value. Let's assume that it's 45 degrees. So this is a situation that we have. Again, similar to what you learned in circular motion, you can see that for this piece of pizza here, or for this arc or this sector over here, you can see that you can form a relationship between the linear distance, the distance of the point of the body from the axis of rotation, and the angular displacement. These three variables here can be connected together through this equation. S is equals R theta. Okay, this is what you have learned in secondary school, and it's what you learned in the previous chapter as well. Again, what we want to be careful about is when we're using this equation here, you have to make sure that you use your angular displacement that is in the unit of radian. Okay, because technically radian is dimensionless. So you can have S and R, which is in meter, S and R, which is in meter, and theta here will be dimensionless. But we write in the radian just to specify that it's a unit for angle. Okay, but technically this radian here is not really a unit, it is dimensionless. Okay, so again, S is equal to R theta, theta must be in the unit of radian. If you have the angle in degree or revolution, please convert it into radian first before you proceed with your calculation. So this is how we relate between S, R, and theta for rotation of rigid body whilst looking at one specific point undergoing circular motion.